Alright, ladies and gentlemen, if you guys remember correctly from our demonstration, the difference between burning sodium and burning magnesium is very clear. Let's check those out again real quickly and discuss why that is. So as we see here in this video, sodium lights on fire in a bright yellow color. As we move, here we see sodium burning on the left, and magnesium, on the other hand, burns in a much different fashion. When we watch magnesium burns, it burns bright white, and in fact, water makes the fire burn even brighter. This is due to a number of reasons, which we'll discuss in a second. So think about it. Why did sodium and magnesium produce very different results when they're lit on fire? I mean, they're directly next to each other on the periodic table. So what is it that sets those two apart, especially when you combust them? We're going to talk about it today in lecture 1.5 on metals, nonmetals, semimetals, and periodic groups. Today we want to focus on identifying an element as being an alkali metal, an alkaline earth metal, transition metal, halogen, or noble gas, as well as explaining how electrons, and in particular valence electrons, lead to these properties. We also want to be able to identify an element as being a metal, nonmetal, or semimetal. So let's get right to it. The main essential point for the day is that elements in the same group have similar properties because they have the exact same number of valence electrons. So if you look at the second group on the periodic table, you'll see that you have beryllium, magnesium, calcium, all directly on top of one another. Each one of these has the exact same number of valence electrons because they're in the same group. They're in group 2. So beryllium, Be, magnesium, Mg, and even calcium, Ca, all react very similarly because they have the same number of valence electrons. And in this case, since they're in group 2, they're going to have 2 valence electrons, each of them. 1, 2, 1, 2, 1, 2. Let's talk about why this matters. My favorite group, one of the coolest groups, are the alkali metals. These are the very first group, group 1A. They only have 1 valence electron. They're also very, very, very highly reactive with water. For this reason, you can't find them on their own in the world because they react with the moisture in the air, and they'll combust oftentimes. Want to see how it works? Check this out. So sodium, when you place it in water, fizzes and burns very evenly. Same with sodium and lithium, both of them. However, if you get to sort of some of the bigger alkali metals, like cesium, watch what happens to cesium. The reaction is so violent that it actually explodes the entire container that was containing the water. Pretty crazy. So we find all of these elements in group 1, right over here. Lithium, sodium, potassium, rubidium, cesium, and francium. And we call those the alkali metals. I'll write that here so you can remember. A-L-K-A-L-I. The alkali metals. The next group we want to talk about are the alkaline earth metals. And these are the ones I mentioned earlier. They're in group 2A or group 2, and of course they have 2 valence electrons. This is magnesium right here. Magnesium is one of the group 2A metals, one of the alkaline earth metals, along with beryllium and calcium, and a few others. They're highly reactive, but they don't react quite as intensely as the group 1 elements do, alkali metals. So we see here beryllium, magnesium, calcium, strontium, barium, and radon all have 2 valence electrons in the second group. The next one we want to talk about, one of my other favorite groups, are the halogens. The halogens are all the way on the right side, right next to the farthest group on the right. Group 7A or group 17, and these have 7 valence electrons. They're the most reactive group because they only need 1 more valence electron to complete their octet and be happy. So they're going to look for that 1 electron wherever they can and react with anything. Check out how they react with aluminum foil. Over here we see bromine reacting with aluminum foil. Let's check out what happens when you put iodine in there with aluminum foil. As you can see, the reaction starts to heat up, and once it gets going, it doesn't stop. It starts to take on what looks like a pit of hell. Pretty crazy. This is because they only need one valence electron to react. We see bromine again here. We find all of these elements over in group 17, fluorine, chlorine, bromine, iodine, and astatine. Then we only deal with the first four. The last important group I want to talk to you about are the noble gases. Noble gases are the ones all the way furthest on the right, group 18, or 8A, and they have 8 valence electrons. Since they have 8 valence electrons, they don't need any more, they don't need any less, they're really happy. It already has a full octet, so there's no reason to react. This is helium, neon, argon, krypton, and xenon. All of them react exactly the same because they have the same number of valence electrons. They're over here. Helium, neon, argon, krypton, xenon, and radon. Now the ones in between, as you noticed before, are the transition metals. These are groups 3 through 12. They have all the typical properties of metals. They conduct electricity and heat. They're malleable. They're shiny. All metals are very shiny. But just look at a fork. So as you see here, this is what the periodic table shows us where all the transition metals are. You take a look, you'll recognize quite a few of them. Zinc, platinum, gold, silver, cadmium, lead, all some of the good ones. So go ahead and summarize that for me for just a second. Pause the video here, write 3 to 4 sentences containing the 4 groups we talked about: alkali metals, alkaline earth metals, halogens, and noble gases, and explain why each of those groups all react similarly. The next thing I want you to think about are the SIM cards in your cell phones. How can SIM cards in your cell phone store so much information and be so tiny? What is it? What are the properties of a SIM card that allow for it to store this much information? So we're going to talk about metals, nonmetals, and semimetals really quickly. Here's some common characteristics of metals. Metals are shiny. Just look at any fork. They're solid, like I said. Just look at a fork. And they're malleable. You can bend them, press them, and they'll permanently stay in that position. They're also really good conductors of heat and electricity. If you stick a fork in an outlet, what's going to happen? You're going to get zapped. The reason why is because metals, the metal that forks are made out of, are really good conductors of electricity. They're also really good conductors of heat. So if you put it on a pan on a heat source, it's going to heat up and cook your food. That's why we use metal pans to cook our food. The other thing we deal with are nonmetals. And these are things that we experience in our day-to-day lives as well. Oxygen in the air, right? They're dull. They're gas at room temperature. They're not malleable, so you can't adjust them, and they don't really conduct heat or electricity. If you zap a taser into the air, the whole room isn't going to get electrocuted. What if it were water? Or if the whole thing were made out of metal, if everyone were touching metal? The reason why everyone doesn't get zapped in a room is because air or nonmetals are really poor conductors of heat and electricity. We call them insulators. The same thing happens if I lit a match in one corner of the room. The whole room isn't going to heat up. It'll take a long time. The heat will be mostly condensed into one tiny little area where the match is actually lit. The last group I want to talk to you about are the semimetals. And these are funky. They contain some characteristics of metals and some characteristics of nonmetals. So when you put them together, you get a few different things. They look like metals, but they're really brittle. They're easy to break. They're also just okay conductors of electricity. And that's why our SIM cards are great for this, because they won't fry anything they're touching and conduct all the electricity, but you can use pathways in the SIM card using binary code to have them store information and data in large quantities, even on something as small as that little SIM card. So if we look on our periodic table, we can find actually where all of the metals, nonmetals, and semimetals are. And the way to do that is by conducting a study on the periodic table. You'll notice that on every periodic table there's something called a staircase. And the staircase looks just like this thing right here. You can walk right down it. Now, all of the metals, all of the elements on the left side of the periodic table, on this side, are all metals. Every one of these guys over here are all metals. On the right side, over here, are all nonmetals. And the ones that are touching the staircase over here are the semimetals. All of them except aluminum. And you'll see that in the way they react with things. So elements on the left are metals, elements on the right are nonmetals, And elements that are touching the staircase, except for aluminum, are semimetals. And we know this because aluminum is what we use to make our cans, our soda cans and whatnot. The one exception to this rule is hydrogen. Hydrogen is located to the left of the staircase, but is still a nonmetal. It looks like this. As we can see, it's red, just like the rest of the nonmetals and the gases. And even though it's on the left side, it is the one exception to the rule. So go ahead and summarize that for me right now. Complete some of the activities for the day. And give yourself a shot in this exit ticket. After you're done, grade yourself on your learning targets. And we're done here. Hope this helped.